Okay, so good afternoon, everyone. Today's webinar is about Sika Stabilizer-500 VCC, a fines suppressing admixture, as probably was the hint in the advert, kind of highlighting this event. And first of all, let's just have a let's just go through the content of the presentation. Obviously, I will discuss the issues of the aggregates very briefly. Possible mitigating strategies, which I think will be known to most of you, the knowledge development and the root of thereof that we've underwent at Sika, both in the UK and also centrally in Zurich. We'll say a few words about the Sika code, newly developed system, and then major on the Stabilizer-500 VCC, saying why it's probably the best performing admixture in the market from robustness point of view. Also, we'll touch on suitability, some performance characteristics, and also we'll show a case study. Obviously, finally, we'll recap and have a Q&A session. So, going into the problem straight away, aggregates. You probably heard that aggregates is the second most consumed raw material in the world. And probably if you guess which one is the first, it will be water, unsurprisingly. And you know, aggregates are under such demand because of urbanization as a main driver of the usage of aggregates. 50 billion tons of aggregates are used annually. Now, looking at the urbanization trends in 1950s, around 30% of population lived in urban areas. Now it's over 55%, and by mid of the century, the number is obviously going to push 70%. Bearing in mind that the population in absolute numbers is growing as well, the demand on aggregates will continue to rise. Also, obviously, the quality of the aggregates is of great importance, and because the extensive usage, we're slowly running out of good sources. The UK is not different. The pressure exists in this country as well. The replenishment currently lagging behind the demand and the extractions, and quality concerns increasingly more common for numerous reasons. No. Sorry. Okay. Looking at the issues that can be with aggregates, I think contamination is the sort of primary example. And why that is, I would say, in a number of cases, insufficient washing facilities. In some cases, it's technically or practically very difficult to do so. And in the right picture, you can see just an example of 20 mil aggregate. It's from one of the UK quarries. I'm going to say which exactly, but that's essentially what, on occasion, we need to deal with. And that's not the worst, to be honest, that is used in concrete production. So in terms of the contamination itself, well, what is the problem? Well, the contamination is caused by the presence of minerals of very small particle size, usually of very high surface area, sometimes with surface charge. They can be swelling, non-swelling. They can have all other performance characteristics, but they can be quite variable in terms of content, but also makeup. This is really important. I'll mention that later on in the presentation. If we use contaminated aggregates in concrete manufacturing, obviously there will be consequences. The most common one and obvious one, workability fluctuation, also a lot of loss of strength, and also durability issues. So what can be done, or what do we do currently when we deal with problematic aggregates, which we just can't simply wash and bring them to the state where they should be? Well, sometimes we can increase the cement content. That approach will certainly work. However, there will be cost and also sustainability implications. Particularly the sustainability being very high on everybody's agenda makes this solution quite an attractive one. So it's not really an option. We can also increase the super plasticizer content. Again, there will be cost implication and also stability issues if that's the approach that is chosen. The third option, or third major option, can be the use of specialized admixture that will negate the presence of this fine contamination. And Sika Stabilizer-500 VCC is one of these materials. That will result in stable concrete in sustainable solution, because we've got also options to reduce cement content in some cases, and will be also cost effective because part of the admixture will replace the existing plasticizer or super plasticizer. So there is a potential for net positive financial effect. Now, I mentioned already Sika Stabilizer-500 VCC being the solution that Sika is offering. Why do we think it's one of the best solutions in the market? It's because of its robustness, and like I mentioned, I will comment on the robustness more later on in the presentation, what it actually means and how we measure that. So before I get to that, I would like to share the journey of the knowledge development. There have been significant resources dedicated by Sika centrally, by our colleagues in Zurich, who studied the contamination matter at fundamental levels, also practically in terms of concrete technology. And obviously, I don't have time to present like all findings, but there will be some conclusions shown in the following slides. So first of all, looking at detection, I mean, very often when we talk about problems with sort of contamination of aggregates, we're also or mostly referring to swallowable fines, to clays. And for that, there is a method, MBV, methylene blue value test, according to EN 933. And that test, obviously, detecting only swallowable contamination, is not really robust enough to detect all problematic scenarios. In the graph, you can see 10 different sands analyzed for flow in mortar, but also analyzed for the MBV test. And you can see, particularly in the examples which are highlighted by the red arrows, that the correlation is not really there, is not always there. For instance, the mortar C, you see high flow, so you would expect low MBV value. Similarly, for the mortar H or sand H, you see very low MBV value, but the flow is not as high as one would expect. So there is no clear correlation between every scenario that will cause problems within aggregates. And to that end, Sika developed a sort of bespoke in-house testing methodology where we can detect actually problems in all cases. I'm not mentioning details because part of these methods are proprietary, but definitely get in touch if you want your aggregates tested for any potential problem. Now, obviously, testing of the issues first thing, then sort of finding out issues of the problem was the next step. So our colleagues in Switzerland looked at potential effects, but also the composition of the various contaminants. And in terms of the effects, obviously there could be those affecting workability in terms of water absorption, such as surface wetting, interparticle hydration, delamination, capillary suction. Low workability due to PC absorption by the contamination. Again, intercalation, that's mainly sort of within the sheets of swallowable material. Surface absorption, delamination as well. And then grading caused low workability, so bad grading, excess fines or lack of fines. Also durability issues caused by presence of various harmful substances. In terms of the composition, obviously from rocks, could be obviously igneous, sedimentary, metamorphic, igneous feldspar, quartz, pyroxenes. Sedimentary could be carbonates, micas, kaolinite, illite, smectite. Metamorphic, pretty much a mixture of the two, depending what the metamorphic rock originates, what it originates from. Various primary minerals, again, as listed in the slide: silica, silicates, phyllosilicates, can be either swelling or non-swelling, also carbonates, iron oxides, sulfides, sulfates. So let's now focus on the effect of the swelling and non-swelling. Like I mentioned, the attention is placed on the swelling clays. Obviously, the effect exists on the non-swelling material as well. So, firstly, effect of swellable fines. So again, you see mortars tested with variable levels of bentonite, which is a swellable material. It's a sort of model scenario where sand was contaminated deliberately with various levels of bentonite. And you can see that the flow table test, as well as the setting time, is dropping quite rapidly with the sort of increasing content of the bentonite. So quite strong effect of on flow and setting time by the contamination presence. Again, that is probably not surprising. Now, looking at non-swellable fines, in this case, the same sand was contaminated with kaolinite instead of bentonite at a bit high level, but the effect, although not so strong, is also quite significant from technological point of view. So it's quite clear that we can have a mixture of contamination. Not all will be swellable, but even the non-swellable or range of other materials that are not swellable will also cause quite a lot of problems. So all the knowledge that was generated both in the UK and centrally has been encapsulated into the system that is called Sika Code. Its information about the system is available online. If you search for challenging aggregates within the Sika system, you will find sufficient or relevant information. It offers approach to solving problems with problematic aggregates, starting with identifying what the problem is, looking at the analysis of the raw materials, finding out what the actual problem is. I mentioned that bespoke Sika testing exists, which obviously we are prepared to deploy to appropriate cases, and then obviously we will design a solution. The system is particularly suitable for very complex and challenging scenarios where sort of standard concrete technology approach will not be enough. And obviously, based on this knowledge, this Sika Stabilizer-500 VCC was developed as well. So what is the specific solution? Obviously mentioned a few times, that's what the webinar is about. Sika Stabilizer-500 VCC. It's an admixture suppressing the negative effects of fine mineral contamination. Sort of fine suppressant is not recognized by, I think, any particular standard, but it would classify as plasticizer according to BS EN 934 part 2. I'll show it's the best performing system in the market. It addresses sustainability by making problematic raw materials useful again. Those which couldn't be used in concrete mixes can now be used with confidence. Obviously, we're achieving cost savings through primarily reduction of issues with concrete performance, decrease in rejected materials, decrease in transport, decrease of the need to handle rejected materials, but also through savings in cement content that does not need to be put on top of the concrete sort of composition in some cases. So I mentioned robustness, I think a number of times already, and now I'll say a few words about it. It's not really as much of a problem to have contamination within aggregates because, like I mentioned, one can design or one can cater for that in the mix design by, let's say, adjusting the proportions of the various raw materials to get the fresh properties as intended. However, what is the biggest problem is the variability of the contamination speciation, but also variability of the contamination content. So let's say if you fix your mix design to certain, I don't know, slump value, and then the next load of aggregates is problematic, what's going to happen? Your workability will be negatively affected again and again and again as more and more or different batches of raw materials are delivered to the plant. So with that in mind, the solution of the sort of 500 or Stabilizer-500 VCC was developed to ensure that as this content of contamination fluctuates, the workability of the fresh concrete stays as stable as possible. And that's where the robustness is coming from, and that's what I'm going to demonstrate in the upcoming slides. Naturally, concrete being very sort of variable material, there is no one solution that fits it all, and pre-trials are always required before the material is used in practical applications. So in terms of suitability of the admixture, it's suitable for natural as well as manufactured sands. It's suitable for ready-mix concrete as well as precast concrete, and some applications not limited to conventional concrete, with pumpable concrete, high performance, self-compacting, slip form, and it's suitable for a broad range of consistent classes, ranging from slump 2 to slump flow 2. Now looking at some of the performance characteristics, so obviously improved virology and improved cohesion properties. Obviously, there is potential to reduce cement content in problematic packages. There is also potential to utilize secondary aggregate sources, again, which will be very, very important going forward when the sort of natural resources of aggregates are being depleted. Improvement of durability, reduction of segregation and bleeding, and also potential to reduce the mixed cost. Some further characteristics of pH 4.6, total chloride less than 0.1%, alkali content less than 0.6, and the recommended dosage obviously will vary from case to case, but typically between 0.3 to 1%. The admixture is compatible with all other Sika admixtures and also with all cement types. And again, pre-trials definitely highly recommended. So I mentioned robustness. Now let's demonstrate what the robustness means in practice. So firstly, on non-swelling fines. So let's imagine we've got aggregates or concrete with 5% of non-swelling fines that would be causing us problems. So we fix our mix design to that 5% as the middle point that you see. Now, the contamination obviously will move up and down, or if it moves up and down, there will be an implication on the workability. So ideally, we would like to be on the 100% dashed line. Yeah, that's our target slump value. If we go above, obviously the slump is higher. If we go below, the slump is less. So if we look at the control, which is the sort of red/orange line, when the contamination decreases, the slump increases, and vice versa. When the contamination increases, the slump is negatively affected as well. So quite a lot of variation. Now, we tested also one of our competitors' product, which improved the situation. That's the gray line. That is closer to the 100%, but Stabilizer-500 VCC is much closer, is the most robust solution. And in the proximity of the 5%, let's say from 4 to 6, the variation is really minimal. Also, what is important to mention, if you look to the top right corner, the control used Viscoflow 1000. It's a popular admixture at 0.85%, and the tested system used reduced content of the admixture, and that differential was made up by the Sika Stabilizer-500 VCC. So there is overall kind of equal amount of admixture going into the system. Now, looking at a similar situation for the swelling fines, obviously the content of the swellable fines is much smaller, because like we mentioned before, the effect of swelling fines is much stronger. In this case, the scenario was fixed at 2%, and again, as we go either down or up, the workability either increases or decreases. For the control, in the most significant way, somewhat less for a competitor's product, and the least for Stabilizer-500 VCC. So that is the demonstration of the robustness of the system. So looking at the case study where this product was used in a quite appreciable quantity. So it was an application of production of 4,005 meters squared of internal floor slab. It was for contractor Fortel at Fleming Way, High Wycombe. Construction started in December 2020, and in January this year was completed. Just an example is shown in the photograph on your right. The conditions were challenging. Not only contaminated aggregates were used of variable level and type, but also was concreted at low temperatures, obviously between December and January. So it wasn't sort of entirely easy scenario. Using any other mitigation strategy wasn't really on the cards because of cost and obviously sustainability issues. But with the Sika Stabilizer-500 VCC, the result was really excellent, and that was a statement from the client, essentially really praising the product for very good performance, as is shown in the slide. So to conclude the initial part of this webinar, so the contamination obviously can vary. It's not only swellable clays. It can be can be a massive amount of minerals that also can cause problems. So we need to concentrate broadly on the issue. And that's what we have done. What we have done at Sika. Bespoke admixture negating the effect is the ideal solution, and the Sika Stabilizer-500 VCC offers the best performance. In terms of the unique selling points, the Sika Stabilizer-500 VCC is the most robust solution on the market, and is based on massive amount of investigation that was done in numerous countries. Obviously, significant impact in terms of sustainability, efficiency, and also cost savings that demonstrably can be achieved. And like I mentioned, if you're interested to use this admixture, always pre-trials are recommended. So that concludes the presentation, and if we can go to the section on the question and answers. I would be very, very happy to answer them. Okay, there is a first one. Why is the performance not demonstrated on real sands but artificially contaminated ones? It's a good question. It would be ideal to do that, or do the investigation or the development on the real sands. The problem is real sands themselves will be highly variable, and for development we need to be able to replicate the systems as best as possible. That's why we use model material that is contaminated with something that we know what it is, and that there is a sort of constant quantity or controlled quantity that we require. Okay, another question. Can marine sand be treated by the admixture instead of washing? The answer is no, because the admixture would not deal with the presence of the various salts that need to be removed by washing. So it would not be a suitable application. Okay, another question. EN 12620 stipulates maximum content of fines at less than 3%. So why did you test up to 8% of fines in one of your cases? Okay, it's very true about the 3% or stipulated in the standard, but that stipulation pertains to 63 micron fines. What our colleagues in Zurich found that fines above that size, up to 125 microns, can also cause similar problems. That's why we've extended that sort of cutoff range into that level, and hence why all of a sudden we deal with way more fines than we would normally originally do.